Section 3.9, we're looking into related rates exercises. For Calculus 1 students, related rates are generally considered one of the more challenging types of exercises involving the application of derivatives. I'd like to include for you here a variety of examples worked through. I'll do a couple on the video as well. I've included the typed lecture notes here for you, where I describe what a related rate is, a general strategy that I provide for you that works. I specifically recommend a good diagram is particularly useful, and coming up with good labels for the diagram. Furthermore, consider that in all of these exercises, as is true for calculus, we're considering things that are in motion. So although our diagram is going to be a static image, just a still frame photograph of what is happening, we really need to envision these things as they are in motion, or as they are evolving and things are changing. We're not only going to be labeling, for instance, the dimensions on our diagram, but we're also going to come up with labels that describe how the quantities are changing. For instance, the rates of change by using the notation for derivatives, most specifically the Leibniz notation for derivatives, dx dt, dy dt, dr dt for the change in a radius, dh dt for the change in a height. And we're almost exclusively we're going to be using t as the input variable that is changing. We can consider that as the variable representing time. So these things are in motion with respect to time. Using the diagram and our labels and geometric reasoning, we would want to connect or relate the variables to each other via equations that we can determine. We want to look out for, if we have right triangles, maybe Pythagorean theorem or trigonometric ratios might be useful. For example, we can create proportions of corresponding sides for similar shapes, such as with similar triangles. Okay, that could be possible, or we could otherwise need to know geometric formulas for areas, volumes, for instance, maybe the volume of a cone or the surface area of a sphere. Okay, so we'll take a look at some different examples again here. We're going to be using implicit differentiation in order to differentiate all the variables, because all the variables included in our diagram will be should be considered to be functions of the same input variable t. In other words, t can be thought of as a parameter that relates all the variables to each other. And then we are going to, after differentiating, then we are going to input the values of the variables that are known at the specific instant in which we're interested in evaluating the related rate. Okay? As a note of warning, we mentioned before in the course that if we are trying to take, let's say you're trying to take a derivative like f prime and then evaluate it at an input like 2, f prime of 2, we would want to take the derivative of the function, let's say f prime of x, and then input 2 into that derivative. Because if we were to input the input value 2, and then take the derivative, we would just end up taking the derivative of a constant, and the answer would be 0. The derivative would just be 0 then. You want to watch out for that same error here in related rates problems. All of our quantities are going to be changing with respect to time, and we're going to be given values for our variables when we're interested in looking at the related rates. Well, we don't want to plug in the values of the variables until after we have done the differentiation, and that's the note of warning. Okay? Let's take a look at some examples. So in the type notes, I include explanations, step-by-step, diagrams, labels, everything that I would want for you to include in your solutions as well. In addition to that, I also give you a worksheet with a few examples here with the answers by the side so that you can practice those. And when it comes to the homework on WebAssign, I've also selected a handful of examples that were available on WebAssign as a tutorial to help step you through the process, step by step, for a few different types of examples. Okay, so we have one here that is the geometry of a rectangle. Take a look at it. The length of a rectangle is increasing. Imagine that, and picture that. Draw a rectangle, but not just a still frame rectangle. We imagine the rectangle is actually evolving and changing. The length of the rectangle is increasing while the width is also increasing. In some problems, you could have that the length is increasing, but the width is decreasing, for instance. Okay, so these things are varying. The dimensions of the rectangle are varying. When the length is 14 centimeters and the width is 4 centimeters, how fast is the area of the rectangle increasing? We're not being asked just what is the area of the rectangle. That would be an algebra question. That's a static question. If we took 14 times 4, we would have the area of the rectangle. We're being asked a calculus question. We're asked how fast that area is changing. All right, how fast the area is changing. Now, it's going to be increasing in this case because, well, we see that the length is increasing and the width is increasing, so we can envision that the rectangle's area is therefore going to be increasing as well. Now, how do we relate these quantities to each other? We have a length and a width, and the product of length and width is equal to area. So you would use an equation, area is equal to length times width, but we're considering that length is a function of time and width is a function of time, because as we imagine this thing evolving, changing, the length and the width, okay, are not constant, right? They're changing in dimension with respect to the time, and the time unit is going to be seconds in this case. So this tutorial exercise will take you through how to solve this for how fast the area is changing. That is, we want to know the rate of change of area with respect to time. So that is, we want to find dA dt. When we are given information about this, the rate of change of the length would be a dL dt. The rate of change of the width would be a dW dt. So how does dA dt relate to dL dt and dW dt when we have a specific value of L and a specific value of W? Okay. A common type of an exercise in related rates is also when we have a volume that is changing. For instance, when we have a tank or a pool, something like that, that is maybe being filled with water, or that water is being emptied out from, or both. Maybe there's water that's being added in to a tank and water that's also coming out of the tank. Okay, I have an example like that in the typed lecture notes that I go through. They're quite complicated to look at, okay? Quite challenging, but they're quite common as well. So I definitely want to include that for you to practice. So here I have one as a tutorial exercise, step by step. How fast is the height of the water increasing? Let's visualize this. We have a tank that's in the shape of a cylinder, okay? And we're talking about the volume of water. So you need to know the volume of a cylinder. That's a right circular cylinder. You take the area of a circle, which is pi r squared, multiplied by the height, which is h. So pi r squared h is the volume of a right circular cylinder. So we imagine that, and we say, we label that the radius is 4 meters. That's going to be constant because it's a right circular cylinder. Okay. It's being filled with water at this rate. You're getting 4 cubic meters of water per minute. Okay. How fast is the height of the water increasing? Okay, so you can imagine that water is being poured into this tank, and the height of the water is therefore changing. And we want to know how fast the height of the water is changing. Another very common type of an exercise is using uniform motion. That's distance equals rate times time. When objects have a constant speed or a constant rate, okay, we can find their distance as a product of rate and time. So it's quite common to have two objects. Let's see, 2 cars, 2 boats, 2 airplanes, for example. Maybe traveling in different directions at different speeds, and we want to find the rate at which the distance between the objects is changing. If you draw a diagram for the situation, you'll get a right triangle out of the diagram, and essentially you'll be using an application of the Pythagorean theorem. You can relate the quantities through the Pythagorean theorem. The length of the hypotenuse would be the distance between the 2 objects, but we're not just finding the length of the hypotenuse. Right? That would be an algebra question. Instead, we would be wanting to know how fast the hypotenuse is changing in size. And it could be that it's increasing or that it's decreasing, depending on how the objects happen to be moving relative to each other. Another type of question that comes up a lot in related rates is where you have a light that is shining, and then there is an object that is moving, and the shadow created by the light interacting with the object is also going to be moving. Right? So we have here a spotlight on the ground shining on a wall, and then there's a man who's 2 meters tall who is walking. And as the man is walking, the shadow is going to be moving as well. And in this case, we have, like, the man is walking toward the building. Okay, walking toward the building, so it's asking how fast is the length of the shadow on the building decreasing when he's 4 meters from the building. Draw a good diagram for this. You should be helped out with that through WebAssign as well. Okay, draw a good diagram and you'll find that similar triangles are going to be very useful here in constructing the relationship between the variables. Okay, and here's another one whereby you have your right triangle and you use the Pythagorean theorem essentially. Okay, so the boat is being pulled into the dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. Okay, so if we draw a horizontal line from the bow of the boat to the dock, okay, then we create a right angle, and this the length of this leg right here would be 1 meter. If the rope is being pulled in at a rate of 1 meter per second, well then how fast is the boat approaching the dock when it is 6 meters from the dock? Okay, so after some tutorial exercises here, I give you a few for you to work out on your own, okay, where you just have to enter the answer. But, of course, I'm interested in more than just what your answer is. I'm interested in the process that you use and how you outline that process on paper. So since I'm mostly interested in the process that you use here, okay, to determine the answers, let's go through some of the processes, through some examples. Type lecture notes. Here we are. A particle is moving along a hyperbola x times y is equal to 8, which is the same as y is equal to 8 over x, by the way. As it reaches the point 4,2, the y-coordinate is decreasing at a rate of 3 centimeters per second. Take a look at our picture here and use the geometry to try to investigate this as this is evolving, this is changing. Okay, we have this in motion. Okay, where we have the hyperbola y equals 8 over x plotted, and then there's the specific point at 4,2. We need to put this thing in motion. So what direction would this point be moving? It's moving along the curve, but is it moving along the curve, towards the left or towards the right? Well, we're being told that the y-coordinate is decreasing. If the y-coordinate is decreasing from this point, then it clearly must be moving to the right. Now that's helpful information, right? We know then we can label now that dy dt is equal to -3, right? We were told it was decreasing at a rate of 3 centimeters per second, therefore dy dt is negative because it was decreasing. But we can see also that on this curve, that then requires that dx dt would have to specifically be a positive quantity because we're moving to the right. We can see from the picture here. All right. Because of the geometry of the curve. If it were a different curve, then it could have been that dx dt was negative instead. Right? Okay, so ultimately we want to find how fast is the x coordinate of the point changing at that instant. In other words, we're asked to find what is dx dt. So, well, we can take the derivative of both sides of this equation or this equation. Right? Take the derivative of both sides with respect to t, considering that x and y are each functions of t. So if we did that with the original equation here, okay, derivative with respect to time on both sides of the equation, well then on the left we would need a product rule, okay, and in that product rule we would have a dx dt and we would have a dy dt show up as well. On the right hand side, the derivative of a constant is just equal to 0. And then after we've done the differentiation, we would plug in the known values of the quantities. We're being told that at the instant we're interested in this, x would be 4, y would be 2, and dy dt would be -3. So we plug those quantities in after we take the derivative. Again, if we plug those values in before we take the derivative, everything's just going to go to 0. And we're going to lose the information, because if we plug the quantities in before we differentiate, we freeze the film, and we want this thing to remain in motion, okay, as we are taking the derivative. Okay, so we wait until after the differentiation is done to plug the known quantities in, and then we solve for the quantity that we were interested in. And we got dx dt is equal to 6 centimeters per second. Notice that is a positive quantity. It came out right from the equation. And that makes sense in terms of the geometry for the picture that we created. Okay. Before we move on to this distance example, okay, let's take a look at another example here on the whiteboard. A particle is moving around the ellipse 4x squared plus 16y squared is equal to 64. At time t, the x and y coordinates are x of t equals 4 cosine t, y of t is equal to 2 sine t. These are parametric equations, okay, which can be used to describe the motion along this ellipse. Okay, if you have any questions about parametric equations, you can set up an office hour. It should be something you've introduced to in a pre-calculus course. Okay, but here you're being given the parametric equations for this ellipse. At what rate is the particle's distance to 2, 0 changing when t is equal to pi over 2? That's going to be very helpful right now for us to get a picture of this. Okay, so try to do visualization. At least that's helpful for me. Okay. So I'm going to draw a graph of this ellipse. Okay, the ellipse 4x squared plus 16y squared is equal to 64. Okay, so to put this into that standard form for an ellipse, we should set the right-hand side equal to 1. That can be done by dividing everything by 64. So dividing everything by 64, we would get x squared over 16 plus y squared over 4 is equal to 1. Okay, since the denominator on the x term, okay, is greater than the denominator for the y term, okay, then we might remember that that means that the ellipse, okay, is going to be stretched out along a major. The major axis will be the horizontal x-axis. In other words, or here's another way to look at it. Solve for the intercepts. If you set x equal to 0, you get y is equal to plus or minus 2. If you set y equal to 0, you get x is equal to plus or minus 4. Okay, so this ellipse clearly stretches further along the x-axis than it does along the y-axis. Okay, so this is the point 4, 0. Okay, this would be the point 0, 2, for example, right? This is negative 4, 0, and this is 0, negative 2. Okay. So the parameterization that was selected here, though, tells us the direction of travel along the ellipse. That is, we note that if t is, for instance, equal to 0, the initial time, then the associated x-coordinate, okay, would be found as what, 4 times the cosine of 0, but that's equal to 4. And the y-coordinate would be, when t is equal to 0, would be 2 times the sine of 0. Well, that's 0. That means the initial point is this point right here. Okay, t is equal to 0, we're at 4, 0. Now what happens as t increases? So for instance, if we let t equal to maybe, how about pi over 4? At pi over 4, then x of t was 4 times the cosine of pi over 4, which is 4 times root 2 over 2, which is 2 root 2. And the y-coordinate of pi over 4 is 2 times the sine of pi over 4. The sine of pi over 4 is root 2 over 2. 2 times root 2 over 2 is just the square root of 2. These are both positive quantities, therefore this point, when t is equal to pi over 4, that shows up in quadrant 1. Okay, so here's another representative point, 2 root 2. Okay, about right there maybe. All right, 2 root 2, comma, root 2. This occurs when t is equal to pi over 4. This helps us put this thing in motion. Okay, so we know that the particle is moving in this direction along the curve. Okay. Now, if we choose an arbitrary point along the curve, okay, an arbitrary point along the curve, let's say this one right here, that's the point x, y. Okay, so we're allowing x and y to vary. We're interested in the distance, so let's imagine that the particle currently is at that position right there, x, y. Right, we're interested in the distance back to another point at 2, 0. So that's not even on the ellipse. So at some point right here, it's the point 2, 0. Okay. So we're interested in how this quantity is changing. The distance between the particle as it moves along this path and that point right there. Right? That distance is going to be changing. So if the particle were over here, of course, there would be a a different distance from the point 2, 0. So that is a varying quantity. Okay. Let's come up with a name for that. We already have x and y being used. We could use d for distance, but I think instead I'm going to use z. Okay, I'm going to use z for the distance here. Okay. Let z equal the distance, okay, from the particle's position at xy, okay, to 2, 0. And so that is changing. Okay. And we're interested specifically in not just what is the distance when t equals pi over 2. That's not what we want. We want to know how fast that distance is changing. How fast the distance is changing when t is equal to pi over 2. Okay. So we want to find dz dt, that's the rate at which the distance between the particle and that point is changing with respect to time, evaluated at t is equal to pi over 2. Now we can find out what x and y are each equal to at pi over 2, right, by simply using the parametric equations here. All right. So for instance, if t is equal to pi over 2, all right, t is equal to pi over 2, then x is equal to 4 times the cosine of pi over 2. Okay, the cosine of pi over 2 is equal to 0, so 4 times 0, which is equal to 0. Okay. And the y-coordinate is 2 times the sine of pi over 2. That's 2 times 1, which is equal to 2. So t is equal to pi over 2 corresponds, using these parametric equations, corresponds to the point with coordinates 0, 2. Okay? So the x-coordinate at pi over 2 is equal to 0. The y-coordinate at pi over 2, that's equal to 2. So these are some known quantities that we have here. Okay. Okay, let's see how we can find dz dt by knowing information about x and y. Well, can we relate x, y, and z to each other? Is there a formula that we can choose that relates them to each other? We can use the distance formula, right, which is really the Pythagorean theorem. Okay, the distance formula. That is that z squared, okay, is going to equal, let's see, x minus 2 squared plus y squared, or y minus 0 squared. Okay, it's really the distance formula. Now, the distance formula, the distance between 2 points, right? If we want to know the distance between the point x, y, and 2, 0, we take the square root, right, of x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula. Okay? Okay, but it's going to be easier for us to do the differentiation if we leave it where all these are squared, right? Then we won't need to take the derivative of a square root. Okay, we can leave it in this form. We're going to be taking the derivative here anyway implicitly. Okay. So now let's take the derivative. Right now let's go try to find out what dz dt is in general, and then plug pi over 2 into that. Okay. So to do that, we take the derivative with respect to time of each side of our equation. Okay. Okay, derivative with respect to time of z squared is equal to the derivative with respect to time of the quantity x minus 2 squared plus y squared. Okay. So on the left, we have 2 times z, and then implicit differentiation, dz dt. On the right-hand side, we're going to have, what, 2 times x minus 2, that's to the power of 1, right, okay, times dx dt. Plus, we're going to have 2 times y dy dt. So we've used implicit differentiation here, right, 3 times. So now the next step is to evaluate, okay, at t is equal to pi over 2. what are we going to have to evaluate? Well, we need to find out what is z at pi over 2. What is x at pi over 2? Well, we found that. That one's going to be 0. What is y at pi over 2? We found that. That's equal to 2. We also need to know what is dx dt at pi over 2 and what is dy dt at pi over 2. Okay. All those quantities in order to find out then what is dz dt going to be at pi over 2. Okay. So let's start solving. Okay. How do we find, let's start with z. How do we find z of pi over 2? Well, we found a way to relate z to x and y right here. All right? Okay, so z of pi over 2 is equal to the square root, it's principal square root because z was a distance, okay, of x at pi over 2, which was 0, minus 2 squared, plus y at pi over 2, which was 2 squared. All right, so in order to evaluate z at pi over 2, went back to our equation here, solved for z, we evaluated x and y at pi over 2, because z, x, and y are all functions of t. Okay, so this gives us, let's see, this is going to be 4, and 4 is 8, so we get the square root of 8, which is equal to 2 root 2. Okay, so z is equal to 2 root 2 when we evaluate t at pi over 2. Okay, what about dx dt? Evaluate dx dt, okay, at t equals pi over 2. Well, to do that, we can find dx dt and then plug in pi over 2. Okay? Well, dx dt can be found, right, by differentiating this parametric equation right here. All right, so we're going to take the derivative with respect to time of 4 cosine t and then evaluate that derivative at pi over 2. So the derivative of 4 cosine t is negative 4 sine t, and then let's evaluate that at pi over 2. So we get negative 4 times the sine of pi over 2. The sine of pi over 2 is equal to 1, so this quantity equals negative 4. So dx dt evaluated at pi over 2, okay, is negative 4. Does that make geometric sense to us as we're watching this thing evolve, by the way? This is saying that the x-coordinate is changing with respect to time. When t is equal to pi over 2, that is, the x-coordinate is changing with respect to time, okay, in the negative direction. So take a look at the picture here. If we imagine our particle is moving along this path in this direction, right, as it passes through this point, notice that it is moving in that direction. The x-coordinate is therefore, right, decreasing because we are moving to the left. If we were to evaluate it, let's say down here at this point, as it passes through that point, the x-coordinate would be expected to be increasing because it would be moving to the right. This is according to the parametric equations that we were given. With a different set of parametric equations for the same ellipse, we could actually change the direction of travel along the curve. But for this pair of parametric equations, that was selected, okay, this has prescribed the motion, okay, the motion in the counterclockwise direction. So as we pass through the point 0, 2, when t is equal to pi over 2, the x-coordinate is certainly going to be decreasing. Okay, so this seems to make sense. dx dt at t equals pi over 2 is equal to negative 4. Okay, what about dy dt evaluated at pi over 2? So we need to take the derivative with respect to time, okay, of y of t. That would be of 2 sine t. Okay, so take the derivative of 2 sine t and then evaluate that at pi over 2. So the derivative of 2 sine t is 2 cosine t, and then we can evaluate that at pi over 2. So we get 2 times the cosine of pi over 2. The cosine of pi over 2 is 0, so we get 2 times 0, so this is equal to 0. So dy dt, when t is equal to pi over 2, okay, is equal to 0. Okay, so here's our equation now. We had, okay, could have canceled out this 2 by dividing everything by 2, but here's what we had. We had 2 times z, where z is 2 root 2. Right, we evaluated it after we took the derivative. That's when we evaluated z. So we get 2 times 2 root 2 times dz dt. Remember, that's what we're trying to solve for here for the answer to this question. Equals 2 times, now we have the quantity 0 minus 2. Well, that's just going to be negative 2. Times dx dt. Well, that's negative 4. Plus 2 times y, which was 2. And dy dt, which is 0. Okay. So here's an equation we can now solve for dz dt at t is equal to pi over 2. Okay, this is already set up for where t is equal to pi over 2 because we've evaluated everything else when t was equal to pi over 2. Okay, so I'm going to solve this for dz dt at t equals pi over 2 by dividing both sides by this quantity. This is 4 root 2. All right. Okay, so we have let's see, negative 4 times negative 2 is 8. 8 times 2 is 16. Okay, and then this is 0, so we have 16 plus 0, and then that's divided by 4 root 2. Okay, so we have 16 divided by 4 root 2, which is 4 over root 2. Or if I rationalize the denominator there, root 2 over root 2, we get what? 4 root 2 over 2, which is 2 times the square root of 2. That's our answer. Okay. That is telling us the rate at which the distance between the particle and that fixed point at 2, 0 is changing. All right, let's go purple. At this point right here, okay, now the actual distance between this point and this point we solved for when we found out what z of pi over 2 was, right? Z of pi over 2 was 2 root 2. Okay, it was 2 root 2. But what we're more interested in here was how fast that distance was changing, and that distance was changing at a rate of 2 root 2 as well. Okay, so that is the distance between the particle and this point is increasing, right? If we were to move a bit forward in time, we would find a larger distance. Okay. Okay, and that distance at this instant is increasing at a rate of 2 times the square root of 2 units of distance, okay, per each unit of time, t. That's a related rate exercise. Okay, so we had to relate the rate of change of the distance to the rate of change of each of the coordinates in this exercise. All right, let's take it easy with the next exercise. This one says each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? Okay. I'm going to start with a diagram representing the situation. The diagram should look like a square. Okay, and that square, okay, we have the sides of the square are increasing. So I'm going to envision this, maybe even put into the diagram a visualization of trying to show that this thing is growing, okay, increasing in size. Let's start with a square. Okay, here's our square. Okay, we have each of the side lengths are increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing? Well, we need to label the sides. Now, a square, of course, has 4 equal length sides. I'll call each side x, okay, in length. The length of each side is now x. And then also I'm gonna try to put, an element of change in here, like an arrow or a vector here. This is our dx dt. That is the rate at which the side length is increasing. Now, if the side length were decreasing, I would have drawn the arrow in this direction instead. Right now, I also would want to put one here, so I'd be showing that the square is actually getting smaller if those two lengths were decreasing. But for this exercise, we have each of these sides are increasing. In fact, all 4 of the sides, of course, are increasing. So this is also a dx dt. Okay, This is equal to 6. This is equal to 6, right? Centimeters per second, centimeters per second. So the units for x are centimeters. The units for t, well, those would be seconds, right? Okay, so after 1 second passes, we would estimate that we have the length. This length would be x plus 6, and this length would be x plus 6, and so we would have a larger square as a result of that. Right, so this is what the larger square would look like, right? It is now the size of the square has grown, and clearly the area would be larger. All right, so I tried to sort of put my diagram in motion here. At what rate is the area of the square increasing when the area is 16 centimeters squared? We need to relate area, okay, to the variables, okay, that represent the side length. Well, what's the area of a square? That would be a is equal to x squared. Okay, let's notate what it is we're trying to find here. Okay, we're interested in the rate that the area of the square is increasing when the area is 16 centimeters squared. Okay, so that is, we're being asked to find the rate of change of area, that's dA, okay, how fast it is increasing, so dA dt. Okay, and we're being asked to evaluate that when the value of the area is 16. That's when A is equal to 16. That's what we want to find. Okay. All right, well, in order to find dA dt, we should take the derivative of both sides of our formula here with respect to time. Okay, so let's differentiate. Derivative with respect to time of area is equal to the derivative with respect to time of x squared. Right, so of course, both area and x are functions of time here. All right, so we have dA dt on the left, and on the right, we're going to need to use implicit differentiation. We have 2x times dx dt. Okay, now evaluate this when a is equal to 16. Well, there is no longer an a in this equation. We have dA dt, that's what we're trying to solve for, but we don't necessarily have a. What we do have is we have x and dx dt. We know what dx dt is. That was equal to 6. Okay, that was given information. But what about x? What is x equal to? Well, we're finding out what x is equal to at the moment that a is equal to 16. So we go back to the equation. A is equal to x squared, and we input where a is equal to 16 in order to solve for x at that instant. So x is equal to 4. Okay. So we plug 4 in for x, we plug 6 in for dx dt, and that takes care of all the variables in our equation. So dA dt, evaluated when a is equal to 16, that would be equal to 2 times 4 times 6. Okay, it's 8 times 6 is 48. 48. What are the units going to have to be? Well, we're evaluating a dA over dt. If the distance was centimeters, then the area would be centimeters squared. And the units for time here were seconds. So we have that the area is increasing. Let's write this out as a statement here. Right? The area of the square is increasing, clearly increasing because the derivative is positive, right? And we can see it from the picture as well. The area is increasing at a rate of 48 square centimeters per second, okay, at the instant when the area is 16 centimeters squared. Okay. So this is how fast that area is increasing at that instant. At a different instant, we would have a different rate of increase in general, right? So again, we could have found x from the beginning. We're plugging in a is equal to 16 to solve for x is equal to 4, and that's fine, but we want to hold off on plugging in the value of x until after we take the derivative. If we had plugged in the value of x as 4 and then took the derivative, we would have just had 0, right? Because we would have taken the derivative of 16. There's another one involving geometry. Here's 3 dimensions, though. If a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay. Starting with a picture for our snowball, let's imagine that this thing is a sphere. Okay, right, so this would be the radius right here, but then this would be the diameter. Okay. We could call it D for diameter, but because the differential operator has D's in it already, I'd rather use a different variable. Okay, so what else do we need to know? So surface area decreases, so we're going to want a variable for surface area. We can use S. The rate at which the diameter decreases, let's just call it X. Okay, so X, okay, I'm going to let X equal the diameter. If X is equal to the diameter, okay, we want to find the rate at which the diameter decreases when the diameter is 10 centimeters. So we want to find the rate at which the diameter is changing. We're told it decreases, so we should expect this to be a negative quantity when we find it. Find dx dt at what instant? When the diameter, that's x, is equal to 10. That's what we want to find. So how do we find that? Well, we relate it to the surface area of a sphere. Okay. Let S equal the surface area of a sphere. Okay, that is S is equal to 4 pi r squared, where r is equal to the radius of the sphere. Now x is equal to the diameter, and the diameter, okay, is 2 times the radius. Okay, so then r is equal to half of x. It's half of the diameter. So we can write s as a function of x now. S is equal to 4 pi, okay, times x over 2, that quantity squared. Okay, and that even simplifies a bit, right? We can square x squared over 4, cancel the 4's, so we get s is equal to pi x squared, right? Where s is a function of time, that is, the surface area is changing with respect to time, and x, the diameter, is also changing with respect to time. As the snowball melts, both the diameter and the surface area are going to be decreasing. Okay, we are given that the surface area is decreasing, right? The surface area is decreasing at a rate of 1 centimeter squared per minute, okay? So we're given that the surface area is decreasing. The rate of change of the surface area with respect to time, okay, in order to indicate it is decreasing, this is equal to a negative quantity. And we're told it's decreasing at the rate of 1 centimeter squared per second. All right, so those units match here, right, with the units in the differential operator here, right, for the derivative notation. The units for surface area are centimeter squared, the units for time are seconds, and the negative is because this surface area is decreasing. So we're given that, okay? And now we can go ahead and find dx dt when x is equal to 10. Okay, so to do that, we take the derivative with respect to time of both sides of our equation. Okay, on the left, that's just ds dt, and then we're going to evaluate that. Okay. You know, this is constant, this ds dt, but we would evaluate it at the time when the diameter is 10 centimeters. Right? On the right, we factor out the pi, and then the derivative of x squared with respect to time is going to be 2x times dx dt. Okay. So we want to find dx dt when x is equal to 10. So we're going to evaluate now at x is equal to 10 centimeters. Okay. Well, ds dt is that constant -1. Pi is constant. 2 is constant. Right? And x, we're inputting 10 for x, and then we're left with dx dt. So dx dt is now being evaluated where x is equal to 10. And that's what we were asked to solve for. So this is what? This is 20 pi. Divide that from the other side. So negative 1 over 20 pi is equal to dx dt when x is equal to 10. What are the units of measurement going to be? Okay, so x is being measured in centimeters and t is being measured in time. Okay, so we have that the diameter, okay, is decreasing, okay, is decreasing at the rate of, now because I use the word decreasing, that already describes the negative, okay, or that already indicates that this is going to be negative. So I want to say it's decreasing at the rate of 1 over 20 pi, right? And the units here would be the units of diameter, which are centimeters, over the units of time, which are seconds. The diameter is decreasing at the rate of 1 over 20 pi centimeters per second, okay, at the instant, okay, when when the diameter is 10 centimeters. That's our verbal description then of what we found. Alright, note, okay, so as I mentioned, decreasing, okay, indicates the quantity is going to be negative, right? It indicates a negative rate of change. Okay, so that's why I did not put a negative in front of this answer here in my verbal description, because I used the word decreasing. The numerical value of the derivative, though, is negative. So this is the correct numerical value that we should choose. Okay, so let's jump back to the typed notes over here. Okay, the next exercise I had here was a uniform motion exercise. Given the information at noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, I constructed a diagram for you. Let's take a close look at the diagram. How did I start? Well, at noon, at 12 o'clock, we had ship A is 100 kilometers to the west of ship B. So the position of ship A is right here at this point at noon, and ship B is at this point at noon. We're not interested in just what's happening at noon. We're interested in what's going to be happening at 4 p.m. Okay. All right. So let's see how this thing evolves. Ship A, starting at this point, sails south. So it's moving south. So I draw an arrow moving south to put this in motion, right? And ship B is sailing north, okay, and they're moving at constant uniform rates, okay, of 35 kilometers per hour and 25 kilometers per hour. So we could say, for instance, we know how far they have each traveled by 4 p.m. At that time, we could say multiply each of their uniform rates by 4, and we can find the actual distance they have traveled, right? So, for instance, ship A in 4 hours would have gone 140 kilometers south. So this distance would be 140 kilometers if we were to freeze, right? If we were to freeze the situation, but we want to allow it to continue to evolve, though, is the thing, right? It's still moving at that time. Okay, so I'm going to want to leave this to be variable for right now. And B, ship B has traveled north 25 kilometers per hour for 4 hours, so it would have gone 100 kilometers north by that time. So we could find out what is the actual distance now between these two ships at 4 p.m. Okay, by finding the length of this side. How could we do that? Well, notice we could create a larger right triangle here, right? The length, the distance that ship A traveled here is the same as the distance from this point down to here, right? And then this length, this 100 kilometers, is the same as this length here. So we could create a larger right triangle here, whereby C is the hypotenuse of that right triangle. Okay? The diagram suggests that we could do that. All right, so that's what I've done here. Okay, in this case, I've moved what? I've moved this length to here, and this is the 100 kilometers. Okay, so we have a right triangle. So now we can see that the sum of the distances that they've traveled, A and B, makes up one leg of the triangle, and 100 kilometers makes up another leg. So we can relate C to the other two sides by the Pythagorean theorem. But we're not just trying to find out what the length of C is. What we really want to know is how fast C is changing at the instant that it is 4 p.m. That is when time is equal to 4 hours. Okay, let's label all the known quantities. We have A, we have B, but also putting this in motion, we have dA dt. What was that amount right there, dA dt? Okay, well, that was 35 kilometers per hour. Okay, this distance here, the distance from this point to here, is increasing, all right, at the rate of 35 kilometers per hour. Okay. And dB dt, the speed of ship B to this length right here, is increasing at 25 kilometers per hour. So dB dt is going to be 25 kilometers per hour. Okay, so now the relationship between these three sides is done by the Pythagorean theorem, right? So we have a plus b quantity squared plus 100 squared is equal to c squared is the general formula, and then we can take the derivative with respect to time of both sides. Okay. Implicit differentiation as well. And then we substitute in all the values at the instant of interest, and that's at 4 p.m., right, which is 4 hours after the starting time at noon, so therefore t is equal to 4, right? So we have after 4 hours, ship A has traveled 140 kilometers. After 4 hours, ship B has traveled 100 kilometers. And after 4 hours, the distance between them would have been 260 kilometers at that instant. So we can plug those values in for A, B, and C. We also can plug in dA dt, which was a constant rate of change, 35 kilometers per hour, and dB dt, which was the constant rate of change of 25 kilometers per hour. Plug all those in to evaluate dC dt, and we get approximately 55.4 kilometers per hour. That's the rate at which the distance between the two ships is increasing. So a good diagram using labels, geometric reasoning in order to come up with a relationship between the variable quantities, and envisioning that your diagram, that things are in motion here, putting arrows on there to indicate the direction of the motion as well. Okay, would be important. Okay, if one of these ships were traveling in the opposite direction, okay, it's going to have some type of an effect, right, on the overall structure of the equation or the derivatives, for example. Let's take a look at a slight variation of this exercise. Almost the same thing, but just a little bit different where the direction of travel is changed. Let's say at noon, their ship A is, well, we have 150 kilometers west of ship B, and ship A is sailing east at 35 kilometers per hour, while ship B is sailing north at 25 kilometers per hour. All right, so it's almost the same exercise. It's just they're starting out at 150 kilometers apart instead of 100 kilometers apart. And ship A, instead of sailing south, ship A is instead going to be sailing to the east, while ship B is still going to be sailing north. Okay, and otherwise we're still asked the question, how fast is the distance between the ships changing at 4 p.m.? Okay, let's come up with a diagram for this situation. Starting at noon, where ship A is 150 kilometers to the west of ship B. All right. So there's ship A initially. There's ship B initially. Okay. And then, and the distance between them is 150 kilometers. So I can label that. Okay, so this is 150 kilometers. All right, and then what happens? Ship A starts sailing to the east at 35 kilometers per hour. So I'm going to use a different color here because so it's overlapping this distance of 150. All right, so the 150 is this distance right here. Okay, but this red arrow, okay, directed to the right, is indicating the direction of travel for ship A. All right, and then what about ship B? So ship B is sailing north, right, at 25 kilometers per hour. Okay, so ship B is going north. Okay, so this is ship B moving like this. This is ship A moving like this. Okay, so after 4 hours has passed, or after, or any time after noon, a certain amount of time has passed, okay, then we are interested in what is the distance, okay, at that time between the two ships. Okay, so this total distance here at noon was 150 kilometers, but that is changing in this way. So we have this right triangle here that we can investigate. Okay, I'm going to simplify this diagram now. All right, here's our right triangle. This is side length B. Okay, this length right here now is going to equal 150 minus A. Okay, where A is the distance that ship A has traveled. Okay, A is the distance that ship A has traveled. I have B is the distance that ship B has traveled. Okay, at time t. So these are each functions of time. All right, so that's B of t, that's A of t. All right, and then this length right here, the distance between them, let's call that C. Okay, so C of t is our distance between ships. Okay, at time t. Okay, so using this triangle here, we can relate these three sides by the Pythagorean theorem. And again, the ship A is actually located at this point, but it was coming from this direction, from some point out here. All right. So this is A out here. Okay, it's not within the triangle, it's actually outside of the triangle that we're investigating here. Okay, but by the Pythagorean theorem, okay, we can relate, let's see, C squared is equal to 150 minus A squared plus B squared. Okay, now we have, let's see, ship A is sailing east at 35 kilometers per hour. Okay, so we have dA dt is equal to 35 kilometers per hour, and dB dt is equal to 25 kilometers per hour. We can find at 4 p.m. what distance has ship A traveled. A of 4, well, that is going to be 35 times 4, okay, which is 140 kilometers. And the distance that ship B has traveled, 25 times 4, that's equal to 100 kilometers. Okay. Now we know the distance that A has traveled, right? But of course this distance, this length right here is 150 minus A. So at 4 p.m., this leg of the triangle would equal 150 minus 140, which is 10. Okay, we're going to find that out from this equation. Let's differentiate though first. Okay, we want to find dc dt when t is equal to 4. So we're going to differentiate both sides of our equation with respect to time, and then we'll plug in the known quantities. Okay, on the left we have 2 times c times dc dt. On the right we're going to have 2 times 150 minus a. Then by the chain rule, okay, we're going to have negative dA dt. All right, because the derivative of negative a is going to be negative as well, right? Plus the derivative of b squared is 2 times b dB dt. Okay. Now let's simplify this. So first off, I can divide everything by 2. Okay, we'll divide everything by 2. Each of our terms. All right, so I can cancel out the 2. And then solve this for dc dt. So dc dt, you can solve for it by dividing everything by c then. So I get dc dt is equal to 150 minus a times negative dA dt plus b times dB dt, and that's all over c. And now we can evaluate dc dt when t is equal to 4. Okay, by plugging in what each of these quantities, a, b, c, dA dt, dB dt, all of those are equal to when t is equal to 4. So that's 150 minus 140, because a of 4 is 140. And then we have negative dA dt, that gives us a negative 35, and that negative is important here, and it's saying that the length of this leg of this triangle, okay, is decreasing, right? The length of this leg of the triangle is decreasing as time progresses because of the direction of travel of ship A, which is taken care of by a well-constructed diagram here with the arrows as well, okay, and is confirmed by taking the derivative correctly here as well, okay. The derivative of this had to be negative. Okay. All right, plus b at 4 was 100 kilometers times dB dt. Well, dB dt was constant at 25, and then c at 4, okay, the distance between them, okay, at 4, all right, we had that before. Do we have that before? I haven't solved for that yet, huh? Yeah. Okay. So c of 4, okay, so c of 4, okay, we can find from this equation here is what? It's going to be the square root of 150 minus 140 squared plus 100 squared. All right, just using this equation here. Okay, let's take the square root of both sides. C has to be non-negative because it's a distance. Okay, A of 4 is 140, B of 4 is 100. Okay, so what does this equal? Square root of a 10 squared plus 100 squared. We can factor out a 10 squared. The square root of 10 squared is 10. Okay, that would leave us with a 1 squared plus 10 squared. Okay, I'm using a factoring strategy here. If we take out 10 squared, okay, that leaves behind a 1 squared plus 10 squared, right? 10 squared times 10 squared would be 100 squared by rules of exponents. Now the square root of 10 squared is just equal to 10. Okay, and then we have the square root of 1 squared plus 10 squared, but that's 1 plus 100, which is 101. So 10 root 101. Okay. All right, so what does this equal? 150 minus 140 is 10. So we have 10 times negative 35 plus we have 100 times 25, right, which is 2500. Okay, over 10 root 101. I can factor out a 10 from the top. Okay. We get negative 35 plus 250 over root 101, which is 215 over root 101. Okay, and let's approximate this to 1 decimal place of accuracy. Okay. 215 divided by the square root of 101 is, what is it, 21.393, so approximately 21.4. What are the units of measure? We just found dc dt, where c was a distance, and that distance was measured in kilometers. The time here is being measured in hours. That was from noon to 4 p.m., where t is equal to 4 hours. So we have kilometers per hour. Okay, so this is the rate of change of the distance between the two ships. And because this quantity is positive, we see then that that distance is increasing. Okay, so the distance, okay, between the ships we found is increasing, okay, at a rate of 21.4 kilometers per hour at 4 p.m. Okay, let's take a look at another kind of an exercise here, one involving an angle. Okay, it's an interesting one. A camera is located 50 feet from a straight road along which a car is traveling at 100 feet per second. The camera turns so that it is pointed at the car as it passes. In radians per second, how fast is the camera turning as the car passes closest to the camera? Let's start out with a diagram and then put this diagram in motion. We have a camera that is 50 feet away from a straight road, and a car is traveling along this road. Okay, and the camera is tracking the car. It's watching the car as it goes by. Okay. Furthermore, we have we're interested in this specifically at the moment that the car is closest to the camera. Okay, so let's say I'll put the camera out here, and the road, I'll have the road moving north-south, for instance. Here's our road. So the camera's watching cars as they're driving along the road, and we're interested in rotation. I'm gonna choose to keep this rotation positive. That is, that I want to keep it rotating in the counterclockwise direction, the standard position of an angle. Okay, the car is closest to the camera. Okay, the car would be closest to the camera. Okay, when this line segment is perpendicular or orthogonal to the road. Okay, so that's the closest. And if I want this camera rotating in the positive direction, okay, then I'm going to say, okay, so let's say that the car is right here, and that the car is traveling north. All right, the car is traveling north. And I'll call let's see, I'll say that the distance that the car has traveled is x. Okay, x is the distance the car traveled. Okay, and therefore then I could say that dx dt is equal to the rate of change of distance with respect to time. So 100 feet. All right, 100 feet per second. Okay, and this is the angle theta right here, right? So we have initially that the camera is pointed in this direction here, but then it's rotating this way as the car moves up, right? As the car moves north, the camera is going to be rotating in this direction. And what we want to find is d theta dt. Okay, at one instant, at the instant that the car reaches this point right here, and the car is going to reach that point right there when theta is equal to 0. Okay. What else can we label here? The camera is located 50 feet from the straight road, so this is 50 feet in here. And this length right here, this is the distance that the car has traveled, right? So x is this length of the triangle. Okay, so now I'm going to simplify this this diagram a bit. Okay, so we have a right triangle. Okay, we have theta right here. This side is length 50, that's 50 feet. This is a right angle. This is x, where x is also measured in feet. Okay, find d theta dt. Well, we need to be able to relate theta to x. How can we do that? Well, relative to theta, x is an opposite side, and 50 feet is an adjacent side, so we can relate them through a tangent equation. The tangent of theta is equal to x over 50. Now we can go and find d theta dt by considering that theta and x are both functions of time. We know what dx dt is, that's 100 feet per second. So let's differentiate with respect to time. Okay, d dt of tangent of theta is equal to d dt of x over 50. All right, the derivative of the tangent of theta is secant squared of theta, and then by implicit differentiation we multiply by d theta dt. on the right, the derivative of x over 50 is 1 over 50, and then implicit differentiation, that means we multiply by dx dt. Now evaluate, okay, at theta is equal to 0. So we get the secant squared of 0 times d theta dt, which is now being evaluated when theta is equal to 0, right, is equal to 1 over 50 times dx dt at theta is equal to 0, but dx dt was constant at 100 feet per second. So this is 100. Okay. Now the secant of 0 is equal to 1, so this is just 1 squared. Okay, so this is 1. So 1 times d theta dt, theta is equal to 0, is equal to 100 over 50. In other words, d theta dt, when theta is equal to 0, is equal to 2. What are the units here? Well, we just found d theta dt, and theta is being measured in radians, okay, and time is being measured in seconds, all right, because we were given feet per second for the motion of the car. Okay, so we got radians per second. Okay, so the camera is rotating at 2 radians per second. Okay. When theta was 0, because when the car was closest, okay, to the camera. Okay, so that's how fast it was rotating. All right. Notice that, I guess, if the car in our diagram was traveling south instead, because it wasn't indicated, which direction it was, if the car happened to be traveling south, then the camera actually would have been rotating in the clockwise direction. And if it was rotating in the clockwise direction, then we would have had d theta dt would instead be -2 radians per second. Okay, let's take a look back at the type lecture notes for one more type of exercise. When a container or a pool is being filled with water, or when it is losing water, or both. Okay, how fast is the water level rising or falling at an instant? So this first example here, the geometry describes the cross-section as the shape of an isosceles trapezoid. So isosceles meaning that the two base angles are going to be equal. So this angle and this angle should be equal to each other. Okay, we're told that one of the bases is 30 centimeters and the other base is 80 centimeters. Okay, and the height of the trapezoid is 50 centimeters. Okay, so we imagine that this in 3 dimensions stretches outward 10 meters. So this creates, a container that is filling up with water, but the 10 meters is constant. So if we can help visualize that. All right, so we have our trapezoid, okay, but then this is stretched outward, right, 10 meters in this direction. So this is 10 meters, right, this is 10 meters, this is 10 meters. Okay, looking at this from above, if you were looking straight down on this thing, you're just going to see a rectangle. All right, from directly above, just looks like a rectangle. But as we can see from the cross section, if you were to, if the water were filled all the way to the top, the very top slice of water, okay, would be a larger rectangle than, let's say, if you took, a slice from down here, all right, where it would also be, it would look like a rectangle from above, but this slice of water would have a smaller width. It would still have a length of 10 meters, but the width is dependent on, where, it's dependent on, in this case, it's going to be dependent on the height of the water, right? The height of the water then determines how wide this rectangle is going to be as we look at it from above. Okay, so here's our diagram for the cross section. We imagine this is also stretching out by 10 meters. Okay, what are we told? the trough is being filled with water at the rate of 0.2 cubic meters per minute. Okay, so that's a change in volume with respect to time, where the volume is in meters cubed and the time is in minutes. How fast is the water level rising when the water is 30 centimeters deep? Okay, now an extra issue that is given to us here in the given information. The water is filling it up at a rate that's measured in cubic meters per minute, but then we're asked to measure the height in centimeters. We're also given other dimensions in centimeters and some in meters. We need to get all of these spatial dimensions to be the same. So we either need to convert centimeters into meters or convert meters into centimeters. Okay. And to be consistent throughout as well. Okay, so here I've converted centimeters into meters. So I've changed the 80 centimeters into 0.8 meters, 50 centimeters is 0.5 meters, and 30 centimeters is 0.3 meters as well. So the height then is going to be, the height that we're going to evaluate this at will be at 0.3 meters as well. We're asked to find how fast is the water level rising. That is the change in the height of the water with respect to time. So we're asked to find dH dt at the time, okay, when the height is 0.3 meters. Okay, so we have the water level here is changing over time. Okay, so let's put this in motion. Here we go. I put the height of the water here in blue at an instant, at an arbitrary instant. Okay, so right now the height of the water height is measured from the bottom, okay, up to this blue line. That's the current height of the water, and that height is changing. Okay, so the blue line is moving up as this thing is being filled up. Okay, we're interested in this situation at the instant that height happens to be 0.3 meters, but we don't want to freeze it there. We want to take the derivative before we evaluate it at 0.3 meters. All right, so we can determine how fast that height is changing. Okay. All right, and we want to relate that height to given information about the change in the volume. Well, how does the volume of our shape relate to the height of the water? Okay. Should visualize this thing again in 3 dimensions. If we take the cross-sectional area, okay, if A equals the cross-sectional area of this thing, in this case the area of this trapezoid is what A is, and then let's call this measure, let's say the length. Okay, let's let L equal the length, okay, of the trough. Okay, then the volume, okay, the volume is going to be equal to the cross-sectional area, right, times the length, which in this case would be 10 times A, because the length is constant at 10 meters. Regardless of what the height is, the length is going to be 10 meters for this shape. Okay, so the volume is 10 times A, where A is the cross-sectional area. But what is the cross-sectional area? Well, it's the area of a trapezoid, and the area of a trapezoid is 1/2 times the sum of the bases, that is the average of the 2 bases, times the height. Okay, where B1 and B2, okay, are the 2 bases for our trapezoid. Okay, and now the base at the bottom is remaining constant. Let's say this one, for instance, maybe I'll call this one B1 down here. That's going to be the same no matter what the height is. But notice, depending on what the height of the water is, the base up here is going to change. We're not taking the top of the trough. We're not trying to find the volume of the entire shape. We're trying to find the volume when h is at any value of h, that is. So we need to find the length of this base in terms of the height. Since it is varying, we have to relate them to each other. Let's dive deeper into the geometry then. Okay. So what I've chosen to do is this. By using the symmetry of this isosceles trapezoid, that is again that this angle, the base angles are equal. Okay, so we can slice off a right triangle on the left and a right triangle on the right, and those 2 triangles would have the same dimensions as each other, first of all. Okay, We can label then what this length is here. Do that on the next page, okay, to help you visualize this. Okay, so if this length right here, I called it x here, okay, and this length over here would also have to be x by symmetry because this is an isosceles trapezoid. And then this length right here, well, that has to be 30 centimeters or 0.3 meters, right? Because this center section is just a rectangle. Okay, now how do we find out what x is? We need to know what x is because then B2, the total length of the blue line here, is going to end up being x plus 30 plus x, or 2x plus 30. Okay, so we want to find x in terms of h. And to find x in terms of h, we can use the fact that this shape here, okay, this shape here is a similar triangle to this shape here. We have similar triangles, and therefore the ratios of corresponding sides are going to be equal. What are the corresponding sides? Well, the smaller triangle, we have x and h. So we have, for instance, the ratio of x to h in the smaller triangle. Well, that has to be the same as the ratio of this side, the 25, to this side. And this side here is the total height of the trough. Okay? And that was given to us as 50 centimeters. Okay, so we have x over h equals 25 over 50 then. Okay, if we keep this in centimeters. Okay, in meters it would be x over h equals 0.25 over 0.5. We'll get the same ratio. Okay, in the end, x is to h as 25 is to 50 by similar triangles. And so we're able to get x in terms of h. So this is h over 2. So back to here. That means that this length right here, from this dotted line out to the left edge, that is h over 2. And we have that on the other side, we're going to have another h over 2. Okay, on the right side by symmetry. So we have 2 h's over 2. And 2 times h over 2 is just h. Then we have this center section for the blue line, which is another 0.3 meters, right? So what is B2 in terms of h? In terms of h, B2 is therefore going to be 2 times h over 2 plus 0.3, which is h plus 0.3. Now we go back to our volume formula then. This was our volume formula for this case. Remember that 5 came from multiplying 1/2 times the length 10, right? B1 was constant at 0.3. B2 is equal to h plus 0.3. Plug those in, we now have volume in terms of h. Okay. With volume in terms of h, we can now go ahead and try to find dH dt. Right? And evaluate dH dt when h is equal to 0.3 meters. Okay. So we take the derivative of both sides with respect to time. Okay, dV dt, we were given that quantity, right? The change in the volume with respect to time. That was told to us that the water was being added to the trough at a rate of 0.2 cubic meters per minute. Okay, so dV dt is 0.2 as long as we are in cubic meters per minute. Remember that means we want to have the height measured in meters as well. So we're going to choose h to be 0.3 here instead of 30 centimeters to choose 0.3 meters for height. Okay, solve for dH dt at the instant when h is equal to 0.3 meters. We now plug in 0.3 as h, we plug 0.2 in as dV dt, and then we solve for dH dt. Okay. All right, so we get that the height of the water is increasing. The height is increasing at a rate of 10/3 of a centimeter per minute at the instant that the water is 30 centimeters deep. All right, I have one more exercise outlined for you here as well, like diagram and fully explained. Okay, for another one involving water, but now we have an extra component. Water is being added to a tank that is an inverted cone, a right circular cone, but also water is leaking out of the tank. Okay, so we have water coming in and another volume of water that is leaking out. Okay, but overall, there is more water being pumped into the tank than the water that is leaking out of the tank, so we still are going to have that the height of the water is rising. All right, so I think that it is probably clear that these exercises can get quite challenging. Okay, I've given you some of the different types of related rates problems you can encounter, but not all of the types you may encounter in the future. But I will be asking you to solve problems that are more or less of these types. All right, and also take a look at the exercises, of course, that you find in the homework. All right, plenty more examples exist online as well. If that's not, if that's not enough, you can always find more. I have plenty of more exercises as well. Let me know if you have any questions, okay, on related rates. Okay, take care.